So we have looked at what gases are, and we've looked at calculations involving pressure, temperature, volume, and number of moles. And we've got some gas laws, of which the most probably important is the combined gas law, because it contains the rest of them. And we know that we have P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. Now, this is the combined gas law. And the question is, when do we use it? We use this when our conditions are changing, when we have two pressures or two volumes, etc. If we have two of something, we're going to be looking at our conditions changing, and we're going to use the combined gas law. So this section instead, we're going to be looking at fixed conditions. And you're going to know you're going to need an ideal gas law when you're only given one pressure, one volume, one temperature, and you're solving for another one of these. So in a sense, we're just going to be using half of this equation. So first of all, let's introduce a set of conditions called STP. It's not a particularly good set of conditions because the temperature is 273 Kelvin. By the way, that's 0 degrees Celsius. For gases, that's bad because that's like when water is frozen. So STP, but not a particularly good set of standards. But the conditions are 0 degrees Celsius or 273 Kelvin and 1 atm. Now, if we take our equation and we plug in such that we have PV over NT, and we solve for whatever constant that is equal to. And again, we know it's got to be equal to a constant because it's going to be proportional to a second set of conditions. P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. That means that ratio is constant. Well, if we plug in our conditions at STP and we put in a pressure of 1 atmosphere and we put in the volume of 1 mole of an ideal gas. So if we are at STP, then 1 mole of any ideal gas, now remember a lot of gases aren't ideal, but 1 mole of an ideal gas at STP has a volume of 22.41 liters. And if we plug this in, 1 atmosphere, 22.41 liters, 1 mole of an ideal gas, so 1 mole down there, temperature of 0 degrees Celsius, but we got to put it in kelvins, we are going to get the value of this constant. This constant, given these units, is 0.08206 units of liters, atmospheres per mole, multiplied by the temperature in kelvins. Now, we tend to work in this particular set of units. So anytime we're using the ideal gas law, which, by the way, is PV equal to nRT, where R is our gas constant, it'll be given on your equation sheet. And if we have this PV equals nRT, what we can do is if we're given 3 variables, R is a constant, we could solve for the 4th one. And this set of units, liters, atmospheres, mole, Kelvin, is going to fix the value of R to be 0.08206. So STP, well, why do we use it? We use it because we know that moles are going to be directly proportional to volume. And if we hold some other things constant, for example, temperature at 273 Kelvin and a pressure at 1 atm, this is going to allow us to directly compare moles and volume. So if I have 1 mole of helium, which weighs 4 grams, it's going to have a volume of 22.4 liters. If I have 1 mole of ammonia, which weighs 15 grams, it's going to have a volume of 22.4 liters. Why? Molar mass is 15 grams per mole. If I have 1 mole of oxygen, which weighs 32 grams, it has a volume of 22 liters. So if we're using volumes in a reaction, we inherently know how many moles of our compound we're going to have at STP because we know that there are 22.4 liters per mole for any ideal gas at STP. So let's do an example. So what is the volume in liters occupied by some HCl at STP? So if we were at STP, our brain immediately needs to tell us that we have 22.4 liters per mole. So if we can figure out how many moles of HCl we have, we know how many liters we have. Well, we can do molar mass. 49.8 grams, 1 mole for every 36.45 grams. And we know that we have a volume of 22.4 liters per mole, assuming that this is an ideal gas. And when we cross out our units, we are going to get that a volume for this gas is 30.6 liters. There's a direct relationship here again between moles and volume. We can do it at any set of temperatures. We simply choose to use STP, 1 atm and 273 Kelvin. So what is the pressure of 25.8 grams of sulfur dioxide? Please note this is a gas at this temperature. We'll tell you that on an exam. Given that SO2 here, it has a volume of 4.25 liters at a temperature of 75 degrees Celsius. So we have pressure that we want. We know how many grams we have a volume, and we have temperature. So our question is, are our conditions variable, two pressures, two temperatures, or two volumes, or are they fixed? If they are fixed, we need the ideal gas law. If they're variable, temperatures of two pressures, we need the combined gas law. So we look at this one and realize that we only have one value for each, and therefore our conditions are, which means that we need the ideal gas law. So if you look up in your equation sheet, and you can remember here that R is equal to 0.08206 liters atmospheres per mole Kelvin. This immediately tells you what units everything has to be in. Our volume has to be in liters. Our pressure has to be in atmospheres. The amount has to be in moles. And the temperature has to be in Kelvin. So let's take and rearrange some of this. If we have 25.8 grams, we calculate the molar mass. We have 1 mole for every 64 grams, giving us a total here of 0.403 moles. Our volume is 4.25 liters. Well, that's in the right units and we're good. Our temperature is 75 degrees Celsius. Well, it has to be in Kelvin. So add 273 and you are going to get 248 Kelvin. So now we plug it in. We have PV is equal to nRT. We're solving for pressure, so we're going to rearrange. We're going to say P is equal to nRT over V, and we're going to plug it in. 0.403 moles from the amount here, multiplied by 0.08206 liters atmospheres per mole Kelvin, multiplied by 348 kelvins, divided by the volume in liters, 4.25 liters. If we take a look at our units, our moles cancel, our volume in liters cancels, our temperature in Kelvin cancels, and we're going to get an unit or an answer in atmospheres, and our P is going to equal 2.71 atm. So when we're having fixed conditions, one pressure, one temperature, one volume, we can use or will use the ideal gas law. All right, we have a couple more equations that we can get from rearranging the ideal gas law. So PV is equal to nRT. Well, if we want density, and when we have density of a gas, we're going to have units of grams per liter. Well, if we're going to go quantity from moles here into grams, we're going to need the molar mass. And our equation here for density works out to be D is equal to the pressure times the molar mass over RT. We can also do equation for the molar mass if we want to do this instead. Well, if we do our molar mass instead, we're going to have the molar mass is equal to how many grams of gas that we have multiplied by RT over PV. All right, so we've got a couple of equations that we can use. These also are on your equation sheet. And you could derive them if you need to, but sometimes it's nice just to have them down and we can just use them. So let's do the density of a gas. We have uranium hexafluoride. This is UF6. By the way, they used to use this to actually separate out uranium, the radioactive version 235 versus much less radioactive version 238 when they're making atomic bombs. So we have UF6. We're looking at a pressure of 1.025 atmospheres at a temperature of 62 degrees Celsius. 62 degrees Celsius, if we put this this in kelvins, we are going to get 335. And if we want density, our equation is right here. We need the pressure, we need the molar mass, we need the temperature, we need R, and we can get our density. So R is equal to 0.08206 liters atmospheres per mole K. If we add this up, we can get a molar mass of UF6 of 352 grams per mole. All right, so our equation is D, our density, is the pressure times the molar mass over RT. If we plug this in, our density is 1.025 atmospheres, multiplied by the molar mass, 352 grams per mole, divided by the R, 0.08206 liters atmospheres per mole Kelvin, multiplied by our temperature here, which is 355 kelvins. Now, notice I put the units in. Let's make sure that they all cancel. If we do this, our atmospheres cancels, our moles cancels, our temperature in kelvins cancels, and we're going to get units of grams per liter, and our value is going to work out to be 13.1. It's going to be dense because that is definitely a heavy metal. All right, so last question, molar mass. Now, if you have a hard time using these, you can always go back to PV is equal to nRT and solve for moles. Moles will equal PV over RT. And if you want molar mass is going to be how much this stuff weighs in grams divided by the N, the number of moles. Or you can sort of stuff it all in and rearrange it, and you'll get this equation down here. So what do we need? We need grams, 0.420 grams. We need the R value. R is 0.08206 liters atmospheres per mole K. We need a temperature. Temperature here is 25 degrees Celsius. We know we need our temperature in Kelvin, so that's 298 Kelvin. We're going to need a pressure. Our pressure is 714 torr. We know from the units of pressure in R that it's got to be in atmospheres. Well, there's 1 atm for every 760 torr. And that's going to give a pressure here of 0.939 atm. And the last thing we need is volume. Volume is 249 mils, but according to our R value, our volume has to be in liters. There's 1 liter for every 1,000 mils, and that's going to equal 0.249 liters. So molar mass is equal to the grams multiplied by RT over PV. So we're going to plug it in. 0.420 grams multiplied by R, 0.08206 liters atmospheres per mole K, multiplied by the temperature in K, kelvins, which is 298, divided by the pressure, 0.939 atmospheres, multiplied by the volume in liters, 0.249 liters. All right, we solved that. It's going to give us molar mass. That's 43.9 grams per mole. The last question you're asked for is which gas is it? It's a compound of carbon and oxygen. Carbon and oxygen has 2 options, CO and CO2. This one is CO2.